All right, welcome to chapter 5 on systems of two linear equations and two variables. So this is section 5.1 on systems of equations graphing. So systems of two linear equations and two variables are such as, we have some ax plus by equals c and another dx plus ef equals f. And what we want to do is use these two equations to solve for some xy ordered pair. Okay, so the a, b, c, d, e, f are all coefficients and our x and y are the variables. And these equations here are called standard form. So that's what we always want to get to when we're solving these systems of equations to start with, and then we'll move there depending on what we have on the method to solve with. And so these are with three solutions to a linear system of equations. If the two lines intersect, so maybe if we have, our coordinate system and we have one line going like that and another line going like that, that intersection is the solution to xy, okay? And it's a ordered pair xy. Now, if the two lines do not intersect, such as they're parallel, so if we have two lines and they're parallel, they're never going to intersect, so there's never going to be something in common to either one of them, then they have different y-intercepts maybe, or they're parallel like this, or whatever, then what happens is there's no solution. Now, if the two lines are the same line, basically they're parallel and have the same y-intercept, so in that case, maybe we have something like that, and there's another line right on top of that. Basically what we have then is infinitely many solutions. And so, every solution you pick is a solution to each of the two equations. Now, if we get one solution, we need to check it in both original equations to verify. So we can do a check here and verify that it works in both equations. And again, use the originals, not anything you've done to them. And if we have no solution or infinitely many solutions, it's really hard to do a check. I mean, with infinitely many, you can choose a couple points and see if it works for both of them all the way through. But the no solution, you really can't. You can't do that. So that's going to be an issue there. So let's show how to verify a solution on this system of equations. So we have these two equations, and they are giving us that as a solution. So we've basically, quote, solved it. This is a solution. Now we have to check it. All we do is we plug it back into both equations. So we have the -5 times, now that x is a -1 plus 6 times 1 equals 11. Well, that's going to be +5 plus 6 equals 11. Well, that checks out. What about this one? 4 times -1 plus 2 times 1 equals a -4. Well, that's going to be a -4. That's going to be plus 2 equals -4. Well, -2 equals -4. That doesn't check out. Okay, so in this case, you must have done something wrong. And this is why you always go back and check it into both equations, because that second one, it didn't work. So, even though we thought, oh yeah, we've solved it, it didn't work. And so that means we've done something wrong somewhere along the way, and we need to resolve the system of equations. And when you do this and have a actual solution, if you get it to work, you have the correct answer and you can't get it wrong. Now, if you go back and it says, oh, one's right, one's wrong, and you still put that as your answer, you're going to get it wrong. So the check is always the ideal thing to do on these cases. Now with graphing, we decide which way we want to graph the two equations. We can plot points. Basically, we choose an x or y value, and then we solve for the other and get a table of points. Or we can solve into the form y equals mx plus b. We plot the 0b point and then use the slope to find additional points. So we use our rise over our run, basically. Okay. Now, no, graphing solutions really only works for whole number solutions. So if we have whole numbers, it's fine. It works really well. But when you end up with fractional or decimal values, other methods are going to be needed to solve and get the precise answers. Because when you get a graph and you're out here somewhere and this is over here is a 2 and over here is 3. Well, is that a 0.4? Is that a 0.421? Or, what is that? So you really can't decide what it is. And so using other methods other than graphing are going to help us if we have anything besides a whole number. Okay. So how do we graph? Well, basically, we plot this equation, then we plot this equation, and we find where they intersect, or if they're on top of each other, there's infinitely many solutions, or if they're parallel, then there's no solution. So that's what we're going to look at working on here. So y equals -3. So it doesn't matter where we put that, it's going to be -3 the whole way. And so we have a line at -3. Well, what about the next one? Well, it's in the y equals mx plus b form. And so let's plot that intercept, 0, -4. So that's going to be our plot hole. And now our slope is -1, which is the same thing as -1 over 1. Or if we want, we can put 1 over -1. So that means we can go down 1, right 1. So we can go down 1, right 1. Or we can go up 1, left 1. Up 1, left 1. All right. And so from that, what we can do is we can draw an line. And it's going to look something like that. Again, drawing is on the computer is kind of hard, so we don't get super straight lines. And so we notice, hey, we have an intersection point there. And what is that intersection point? Well, it's -1, -3. And so that's what we say is our solution to this problem. Now, is it really? Well, let's plug it in. Y equals -3. So if we plug in -3 here, -3 equals -3. That one works. What about the next one? Well, we plug in -3 equals, now we have negative and -1 minus 4. Well, that's -3 equals 1 minus 4, and -3 equals -3. That works as well. And so we're pretty sure that that is the correct answer for this problem. All right, let's stop there and we'll come back for more.